Right, so this is our last lecture on foraging, um, social foraging in particular. So that means I've got UCEs due for you for Unit F and Unit G. I know I've been late on these. I'm going to finish them this weekend and just push the due dates out and give you 2 extra drops this semester to account for my tardiness. So that means is that instead of the UCEs being lowest 5 drop, it's just going to be like lowest 7 drop. So there's a lot of you could just stop doing UCEs probably for the rest of the semester. But I still think they're good for studying, so they'll be available for that. But so they will. See your question. I will get those out, but again, I don't want to pile them up on you. That's why I'll add the extra drops, and I'll push the due dates probably on the next couple. We only have a couple more anyway. Out a little bit farther so that you can kind of divide your time amongst them. So sorry, just this course is just kind of getting ahead of me and getting all the content ready. And I apologize for not being able to get those UCEs out in a quicker way. But yeah, doing my best, and I'll again try to push things out so that it's not an undue burden and there's still an opportunity for you to do them. Question. Bases, because I've been getting those out on time, then I'm going to leave that the standard policy lowest 2. But you said these are the Canvas kind of quizzes. Yeah, so that's right. I'll just right now there's an automatic policy in Canvas that it finds your lowest 5, and whatever one benefits your grade the most, it drops those. I'm just going to increase that to 7. Okay. I may not for me, I may not reflect that on the slides just so it's easier for me because it's imagine I'll probably be teaching this course in fall 2025. And so it's a good chance I'll forget that I did that. I'll come to a lecture and then it's going to have this updated policy, and then it'll be this awkward thing. Well, so I actually don't trust that. So I'm probably going to, the slides will probably be as originally intended, but as special treatment for this semester on Canvas, that additional policy will be added. Yep. F and G are both going to be available. I'm gonna make those available. Just at this point in the semester, normally F would be over with, which is why it's not on this slide. But because I've been tardy in getting it out, I want to give you the ability to practice on them. But it's going to basically turn them into a practice assignment because if you've already done 3 UCEs that you're happy with your grade, then those are going to be your UCE grade. So at that point, it's you can take it and you'll get a score, but I'm going to be dropping most of those UCEs by changing this 5, which was the normal number, to a 7. And then I think I'll be back on schedule to get out for the next units, the UCEs on time. I just had a bunch of things pile up at Unit F and have just been kind of working on a backlog since then. Other questions about the admin stuff? Then, of course, the big thing, though, that I want you to be thinking about, not the UCEs, but I copied this. Well, no, this is good. Yeah, right. So yeah, so this organism in contact. Some of you have already submitted these. Thanks for that. Get those in by Friday. We'll start taking a look at them. So if you want to make any updates, feel free to do so as well. Then we'll take a look at them Friday and get you some feedback. So I think Anushka is going to take a first pass in looking at those and then flag any ones that need me to sort of take special. Then I'm going to sort of wipe or wash back through them as well and make sure that you you the most amount of feedback. And it's as long as you've got sort of as long as you've made an attempt that where you've picked an organism and you've picked, like, it might be we have feedback like, well, I think you should pick something more specific, but you're still going to get points. But you'll just have that feedback that going into your final project, you're going to be more successful if you have a more specific hypothesis. So don't worry about getting it all right, or like the feedback is really meant to be feedback. It's not meant to be like I'm not. You'll get points for sort of putting thought into it and coming up with an animal context combo, but then the feedback might be that we're expecting you to make some changes for the final submission, but that's not going to necessarily take points off for this. So don't stress too much about this. This is your opportunity to communicate with us what you would like to put together for your pitch proposal at the end of the semester. Okay. Questions on that? Pretty clear. It's a group assignment. Only one person in the group needs to upload it. Okay, great. So this is where we left off last time, kind of tragedy of the commons, animal style. And so the idea there was that if you have animals forming groups, then there can be public goods that are created for small group sizes. So there can be bats that come together, and due to eavesdropping effects, it's possible that two or three bats, or two wolves or three wolves, might do better in foraging returns than just one. But the problem with this is it's open to exploitation. So what you end up happening is that you might have reached your optimal group size G star here, so three bats, three wolves, whatever. But then if you have no way to keep anyone out, someone else is going to come in because it's better for them to degrade your group than to go alone. So you get those that sort of are parasites on your public goods until eventually the group good goes down to pretty much the same as the individual good, and it kind of degrades everything in there. So if you have a way to prevent others from entering, then the group sizes you observe in nature will be closer to G star. If you don't have a way to prevent individuals from entering, then the group sizes are closer to G hat. Sometimes in the human literature, G hat is called the open access equilibrium, because this is effectively an open access or a common pool resource. And in reality, when we observe group sizes in nature, they are generally distributed across here, except for that interesting case of wolves that I mentioned last time, where they have group sizes that are way over here, apparently due to the effects of scavenging birds. So, but this is kind of where we started, and we're going to build off of this to move towards from exploitation to competition and cooperation. So, were there any questions about this image here, this figure, this basic idea, or what I mean by kind of tragedy of the commons animal style? So if you've taken any, like a lot of times you hear about fisheries and similar sorts of natural resource management, those are common pool resources, and they almost always in human applications have a very similar looking graph like this, where it's a collective action problem to try to keep humans at the optimal exploitation level. But if you have no way to keep humans out, then you end up getting the open access equilibrium. Same thing happens with animals. Okay, so let's build off of this. All right, so we know that with no barriers to entry, let's just assume we're in that case, that animals are, oh, look, I made this funny word. I spelled it with different letters, free to move around wherever they want. So we have no way to keep animals out of our group. In that case, we would expect to see group sizes that are either at this open access equilibrium, G hat, or a bunch of animals going it alone. So that's when we kind of expect to see in nature. So we would sort of view this as kind of an exploitative equilibrium. These are a bunch of animals joining, trying to exploit the public goods from others and end up depleting all of them. And then we view this one here as just all the other individuals that don't want to join these kind of broken groups, so they end up kind of going it alone. So we get these two here. All right, questions on that? Is that pretty clear? Yeah. Yeah, but great question. So what comes first? So before any aggregation happens, then you're going to have animals that start aggregating with other animals, because it ends up being better to go from a group of one to a group of two. And then they go to a group of three or what. And in this particular case, once that group bubbles up to a size of six, then the seventh individual doesn't have any, or if you get a seventh that joins, either they're going to immediately leave or someone else is going to leave, because it now is worse to be in the group than it is to go alone. So in the transient case, you'd imagine you get these assemblies of these six animal groups, six wolf packs, something like that. And then at that point, there's no benefit to going it alone versus the group. So you may as well go it alone, because if you join this group, it's actually getting even worse than going it alone. Clear? All right. So freely moving animals, in this case, have self-assorted into different aggregations in the habitat based on local productivity. That's interesting. It's this interesting kind of self-organized phenomena that due to just the dynamics of the returns that each animal gets and the sort of frequency dependence on those returns based on what other animals are doing, then it causes this natural sort of segregation into a group of foragers and a bunch of individuals. All right, so what more can we do with that? Well, let's imagine that it's possible to form a second group far enough away from the first group that isn't going to have any sort of interference effects with that first group. But as an individual, you can choose to go over to that new area with that new group. You're free to move over to that new area with that new group. So you got a group way over there that's off foraging. You got a group way over there that's off foraging. Then we can ask, what's going to happen to the group sizes in these two groups that are separated from each other? So initially, I've got this one group over here that's got 6 animals in it, and then it's got these 2 lone animals. I guess if I revise this, I could maybe put some space in between them. This isn't meant to say they're a group of 2. It just means that there's 2 animals that are foraging on their own. So they're alone. So I got these 2 here, but now there's this other foraging opportunity. So what's going to happen? Well, uh, you would expect that if they're free to move, that some of these individuals, the loners, as well as perhaps some that were in the group, might choose to join this other group. So we had 8 animals, and originally those 8 animals had 6 in a group and 2 alone, and everybody was getting roughly the same payoff because there were so many animals in this group over here that the payoff was really no better than going it alone. But now that we've opened up this other opportunity and there's still only 8 animals, then a couple of the animals here go and form a group in this area out of the way of this group. And then this group is doing better than this 6th animal group. So a couple of these also move over. So now I get 2 4 animal groups. And both of these 4 animal groups are doing better than the individual. So the equilibrium fitness here is now actually higher than going it alone. So this was a process, an exploitative process that before led to kind of a tragedy of the commons. Somehow we've resolved the tragedy of the commons. And before I said the only way we could do that is to limit group access. Well, we kind of have limited group access. What is keeping these groups from descending to the open access equilibrium where there's no benefit to being in a group? Any thoughts? What's making this magic happen? Why are now these 8 animals all doing much better than they were when there was only one group? Yeah. Well, that's true. You've effectively added more resources for sure. But I guess the key is that and something else. We've added more resources, but we haven't added something else. So what is keeping, even though we've added resources, what is keeping these groups from growing farther to the point where they're overexploited? Yep. Haven't added more animals. There's a finite number of animals, and it's small enough that we can maintain these groups at this high return rate. So it's like a natural way to manage this collective action problem is just, you know, add more resources, but don't add a whole lot more consumers. And so if you have a small group of consumers, you get sometimes a natural way to deal with overexploitation. In other words, there's no, before when there was only one group, there were too few resources effectively, and so you necessarily would overexploit. Now there's so much resources that you can't overexploit. You're limited by the number of consumers, and being limited by the number of consumers allows every consumer to actually do a lot better on their own. So that's kind of an interesting result. So now we've got a self-organized process that has led animals to split into 2 distant groups from each other, where all of the animals in those groups are doing better than going it alone. So, so that's, I don't know, that's kind of interesting. So we've got animals that are free to move to an ideal group, and that ends up causing them to distribute into these 2 groups that are better than doing it alone. Yep. Um, That's a good question. So the two is better than one is kind of was like the next slide. So here we're sort of suggesting that this is such a small area that there's no real opportunity to form a sort of a separate like group foraging. It's like if they're sort of compressed on a small area, like there's the if this is a public good, like an exploitation sort of thing, like if the benefit you get from joining a group is like the bats, where the only benefit to joining a group is by eavesdropping on another bat, then it may be impossible to sort of form your own group because this group is so close by that they're going to hear your calls. So the only real way to sort of uh, to join your own, the only real way to kind of to prevent from joining this group and dropping below this is by going elsewhere. And you're kind of anticipating what I've just done here. As I said, that I'm like if I'm putting them in a laboratory where they're stuck in a room this size, there's really no way to form two groups because they can all hear each other. But if I open the door and I now allow these animals out, then at that point, like this might be like I said, call this group size, but we could actually say this is maybe social echolocation, and this is maybe foraging on the ground or something like that. But once I open the door and I allow these animals, these bats or whatever, to go anywhere, then they can do, I think, what you're suggesting, form their own group where they get these better benefits. But now they're able to get exploited by those over here who feel like they're losing out. And so then two of these end up joining a group with them, and then it balances out across this. Does that answer your question? And then actually just sort of motivating something else. So this is a little bit of an artificial example in that I've gone from this optimal group size to optimal multiple group size, but I'm going somewhere with this is the reason why it seems a little contrived, but I'm trying to go from what we did last time to what we're doing today. Question, yeah. Well, say that's an excellent question. So this is assuming that these animals are free to move to their ideal location. The mechanism by which that happens, we're taking for granted. So hypothetically speaking, what we're building here are explanatory hypotheses that operate at the functional level. So if you happen to notice, why are there four bats over there and four bats over there? This helps answer that why question. Oh, the function is that if there were six bats and two bats, that actually would be worse off in terms of benefits and costs. Whenever we have benefits and costs, whenever there's fitness, utility, those sorts of words, that's an ultimate explanation, a functional explanation. But that question of, well, how the hell did they go from here to there? That's a mechanistic question. And so that is really important because if you try to publish things like this, then the next question people ask is, all right, if I assume they have the ability to do that, I buy that this is going to happen. But do we know that they have the ability to do that? And then that's like another study to say, how are these animals detecting that their returns are better there? And you might notice that occasionally an animal will leave its group and go elsewhere, and then it'll come back to the group. We're like, well, why did it leave its group? Well, it might have been information foraging. It might have been looking for additional information, and then it might have found another group that it was stuck here. But if it didn't find anything, you just go back to its old group. So that would be one explanation for how this is happening. But we're kind of skipping over that, assuming there is some mechanism that allows them, and I'm using these words so they can burn into your head because they'll be important in a second, so that they are free to move to their ideal location. Yeah, no problem. Well, they weren't, they were alone here. It could have been that the ordering of this could have been different. It could have been that when I opened the door and allowed the animals out, that two of the like several of these, like maybe four of these original six went over, leaving two spots available here and these two went here. So I didn't mean to sort of stipulate that it had to happen in the order that the orange went over and then the blue. It could have been the blue went over and then the orange filled in the gaps. Hmm. Well, so here we're talking about just standard foraging behavior, not we're not assuming these animals are migrating and then going somewhere else while they're migrating. We're saying that if an animal's in its home territory and it's just going out for its standard meals, the quail running around on the ground, and I just happen to notice I see groups of like three quail, three quail, three quail, and I'm like, why aren't there ever six quail? And then like, this would be an explanation for why aren't there under six quail. Mhm. No problem. All right. This is just sort of a motivational example building off what we had last time. Any other questions about that? Or at least getting here? So we got two groups of equal size getting equal benefit to each one of their individuals. All right. So, okay, that's fine joining groups. But there are other things that animals could join. They could join patches. So if we think about ducks on a pond, so here's ducks in a pond in a park. Here's remote banks that are out here, and we can imagine that these ducks in the middle of the pond, they collect their food from the edges of the pond, and there's two places you can collect food: a patch one and a patch two. So if you're looking at ducks on a pond, you're out at Kiwanis Park or something like that, and you see these ducks, around the edge of the pond, you might happen to notice that there's a large aggregation of ducks here and a smaller aggregation of ducks here, but there's definitely ducks in just these two areas. And you'd say, how can I explain the group sizes that I see here? And then the question is some of the logic that we just worked through that was built off of the optimal group size in the exploitation literature, does that actually perhaps give us some insights in how animals are distributing themselves across the habitat here? So that's sort of the question that we're motivating. And this sort of brings up this whole section of animal behavior called habitat choice or habitat selection, how animals distribute themselves in space and time with respect to resources in the environment. So what is the resource distribution here and there that might explain the distributions that we're seeing with the ducks here and there? So let's think about how, well, what could generate these sort of properties, and there are two competitive properties that are feedbacks on animals when they find food that potentially multiple of them can get access to. And one of them is called interference competition. This is when an animal gets access to a resource and prevents another animal from getting access to that resource. It gets in the way. So an organism physically restricts another's access to resource. That's one of them. And so that can create kind of a benefit to those that get to the resource first. And then as more get to the resource, they have more ability to prevent others to access the resource. So this is not necessarily that you're using up all of the food, but let's just say that you get like a nice juicy edge of some sort of food item that you can only eat from the edge in. There's plenty of that food item for everybody, but there's not enough edge for everybody. So as once you get all these animals lined up around the edge, foraging from the outside in, then others just can't get into it, even though there is technically enough food. That's one simple example of interference competition. Another type of competition that it might apply is scramble competition. In this case, it really is a finite resource that can't feed all of the animals at once at the same high level. And so the first ones that get there are going to be able to eat more of it. But if everyone arrives and everyone manages to get access to it, then they might deplete what all of those have access. Like it might be that like instead of one animal getting a huge meal, every animal will get a small fraction of a meal. So scramble competition is when you have too little food, you've discovered a food cache that's too small for the number of animals that are trying to eat from it. A little bit like the scroungers coming to those tiny little patches that the producers have found. The producer had an advantage, that finder's advantage, that A in that equation, and then the scroungers then, though they depleted the rest of the food that the producer could exploit. So two forms of competition that this both applies to. You could have those sorts of things happening in these two patches. So we might model that, given in mind that competition, with similar sorts of curves as we've seen in the group size stuff. So now I've got intake rate to each individual on the y-axis and the number of individuals in those patches on the x-axis. And so the idea here is if one animal came there, let's say it's ducks on a pond, if you're throwing in 5 breadcrumbs per minute, and you're not paying attention how many ducks are there, you're just throwing in every minute 5 breadcrumbs, then one duck is going to have, if they're just sitting in front of you catching, then they're going to eat at 5 breadcrumbs a minute. But if there's 2 ducks and one duck eats, and as it's eating, handling time, another duck swoops in and catches every other one, then the 2 ducks are going to eat around 2.5 breadcrumbs a minute. Once there's 3, it keeps going down. So this is basically 5 divided by 2, 5 divided by 3, 5 divided by 4, and so on, and you get this nice hyperbolic relationship. But we've got somebody else on the other side of the pond also throwing in at 5 breadcrumbs a minute. So they're here. So then you have to say, if you're a duck in the middle of the pond, where do you go? And you can see the ducks, you can see the breadcrumbs, and you can see how quickly they're coming in. Or you might be eating there and you might come there, you just don't get any breadcrumbs after a while. Then you might decide to move. And so we can kind of do the same game where we've got, this divvying up process happening. So the first duck arbitrarily goes to patch 1. It's eaten a lot. The other ducks notice that that other duck is eating a lot, notices that there's somebody else who's also feeding. So the second duck goes over to the other side of the pond. Now they're both eating fine. The third duck comes by and arbitrarily at this point, because it's sort of a symmetric decision, just decides to go to patch 2. So now there's 2 individuals at patch 2. And at this point, that's depleted the intake rate of the original duck that went to patch 2. So now if you're the 4th duck, where do you go? Do you go to patch 2 or patch 1? How many people say patch 1? How many people say patch 2? So which one's got the higher intake rate for the next duck? So if we look at this, we say here, the next duck, this is the current intake rate. If you add another duck, we get roughly 2.5. This is the current intake here. If you add another duck, you get less than 2. So if we're going by intake rate, then that suggests that when you go to 4 ducks, then you should go to patch 1. And then the 5th duck, it doesn't really matter. But then the 6th duck, it's pretty clear that you're going to get better off at patch 2. So now you've got 6 ducks distributed equally among these 2 people throwing breadcrumbs in from 2 sides of the pond. Questions about that? So we just assumed the ducks were free to move to their ideal patch, and they naturally distributed themselves. So we had equal patches, divided the ducks equally. So there was a natural matching that went on here. Okay. Good. So let's now make it more interesting. And let's say that the person in patch 2's spot they are stingier. So they throw breadcrumbs in at 3 breadcrumbs a minute instead of 5 breadcrumbs a minute. So now we have effectively a high quality patch and a low quality patch. Now, when I'm saying quality here, I'm saying regardless of how many ducks are in it, this is a richer patch, patch 1, than patch 2. As more ducks get in it, it makes it harder for other ducks to experience that richness. But fundamentally, intrinsically, patch 1 is a better patch, is a higher quality patch than patch 2. So we have to see then how that then shifts this distribution. So we play the same game. So the first duck is clearly going to go to patch 1 because there's more breadcrumbs coming out to patch 1. Second duck, well, actually here, 2.5 versus 3, it's actually better to go to 3. There might be some noise in the system, and so due to perception error or whatever, the duck might go join patch 1. These are pretty close together, but let's just say most of the time goes to patch 2. But now the third duck, I think it's a pretty clear choice that the third duck probably should go to patch 1 because this, which is here roughly 2.5, is definitely a lot better than this 1.5. And so you play the same game back and forth. And so we look at this next one, and actually, this is interesting. Seems to be above 1.5. So adding a duck here actually gives me a higher rate than adding a duck here. This is close. I mean, this is 1.5. These two are definitely close to each other, but this is higher. So the third duck ends up going to patch 1. Now, at this point, when I say, well, what do I do? So I'm sorry, I meant the fourth duck. the fourth duck goes into patch one. So now I have three ducks in one and only one in patch two. At this point, the next duck, the fifth duck, now patch two is a better, even though patch one's higher quality, now patch two for this number of ducks is better. So the fifth duck goes into here, but then at this point, then for the sixth and final duck, it's actually a little better to go back to patch one. So, and you can imagine, I could have made this much higher quality. I could have made this 10 breadcrumbs a minute and 2 breadcrumbs a minute, and this effect would be even stronger. So the point here is that this is patch one is almost 2 times better than patch two. And at equilibrium, we got roughly twice the number of ducks at patch one that we did at patch two. And they all end up having roughly the same intake rate. So even though patch one is higher quality, um, every duck in the pond is being fed with the same amount of food or is getting the same intake rate. So it's not better to be at patch one or patch two because everything's shook out because, at the point where it becomes worse to be at patch two, you just go to another patch. If you add more ducks, it's going to hurt everybody because the next duck is going to go to the next best place to be. That's going to make it worse to be there. And there's going to be this race, and all of the patches will chase each other. And so things that come to equilibrium and across the whole pond, it doesn't matter where you are, you're getting the same intake rate. Question. Well, yeah. So this model is assuming, and I'll list the assumptions of this model in just a second. But I mean, Gesundheit, it's basically assuming that there's some intrinsic quality that degrades as you add individuals to it, assuming that every individual has sort of an equal competitive ability, so each individual benefits the same way, and assuming every individual is free to move, it knows what its ideal patch is and is free to move. Then this is the prediction how you would get them to line up. And we're going to see how well this prediction works in just a moment. So questions about how this works here? Follow that so far? All right, so this is what's called the ideal free distribution, or the IFD. So that's why I've been using those terms. Unfortunately, in the book, if you were to look up ideal free distribution, I don't know, some mistaken editing or something like that. In chapter 12, where they talk about this kind of habitat distribution, habitat choice, and territoriality, and so on, they have the wrong definition of the ideal free distribution. Trust me, not the book in this case. If you don't believe that, just look it up on Wikipedia or look at any other animal behavior book, and you'll find this definition above me here, is that, this is a matching between resource availability and social allocations. And those of you who've maybe taken a psychology course or just remember back to our operant conditioning, there are Skinner boxes, and I guess I could have put an image of that in here. Maybe I'll think about putting that there. But those Skinner boxes where you have a single animal is pushing levers, you can make one lever reward the animal more often than another. So when you hit the lever, it only gives you a food every third time you hit it, versus the other one where every time you hit it. Well, you're going to get food from both. And what the animal does is it divides its time according to the reward rates. It matches. So if you get 3 times the food out of lever on the left versus lever on the right, it spends 3 times its time hitting the lever on the left versus the lever on the right. And that's called the matching law in psychology. This is the social extension of the matching law, where instead of having a duck going back and forth between 2 patches, every duck stays in one place, but you get more ducks in the area that has the higher reward rate. But it works basically the same way. So if you take an individual who they're the only one there, then they probably would, go around the pond. They would try to exploit as many patches as they could, because if you're not getting a reward here, even if it's more frequent, there's an opportunity cost. So you may as well try for the one you can very quickly get to, that you might get more reward, and that way you can maximize your exploitation. But then you'll have to balance your time out. And that's what the birds do in a Skinner box. But here, the ducks on the pond, they distribute out socially. But it's just a social matching law, the ideal free distribution. So, and notice that as I add foragers, it just pushes this equilibrium line down. So the ideal free distribution is such that every duck will get the same intake rate regardless of where they go. What changes the intake rate is the number of ducks. As you add more ducks, the intake rate for everybody goes down. It's like you're pouring ducks in from the top, and they're sort of filling these in. They fill this one here, and then here, and then here. You could count these off: 1, 2, 3, 4, 5. So you got to count the order at which they're going to exploit these. And if you can reduce the number of ducks, everybody's intake rate goes up. If you can increase the number of ducks, it goes down. And this is how we often plot these. We refer to these lines as suitability functions, and we plot them all together, and then we plot a horizontal line across, and then we sweep the horizontal line up and down, and we watch what populations pop out. And if we know there's 100 animals that we're trying to account for, then we find the horizontal, where the horizontal line goes, where we get 100 dots here. And at that point, we say, aha, that's the distribution we'd expect if they're allocating according to the IFD. Questions about that? All right, now this IFD has some assumptions that it's the predicted distribution if you've got animals trying to minimize resource competition. I'm not expecting you to read all this right now. This is just there to be a reference, but the key highlights here, we're making a super important assumption that animals are free to move to the patch that's ideal for them. If there's something in the environment that's preventing animals from doing that, then that is going to upset this distribution. And we'll talk about an example of one of those things here in a second. We assume that all animals are competitively equal. So every animal's got an equal ability to exploit every patch. We assume that the quality of patches depend only on the amount of resources in it. The suitability declines with the number of animals. Equilibrium occurs when the suitabilities are all about equal and low. And then sometimes if you don't have enough animals, the really crappy patches no one goes to because there's not enough animals to need to go to them. And sometimes we refer to those patches as being truncated. So you'll have across every patch that's exploited, the intake rate will be the same. But really crappy patches that can't reach that intake rate, that's the same for everybody else, don't have any animals. So that's why I have to be clear that the intake rate is only equivalent across patches that have individuals in them. Patches that are too crappy to have any individuals at that population size, of course, can't reach that intake rate. So like if we only had one animal, then patch 1 would be exploited, but patch 2 would be truncated. Okay. Questions about that, the IFD? We can use the IFD to introduce a more general concept called the Nash equilibrium. And so an IFD is an example in social modeling of a so-called Nash or Nash equilibrium. And this and this will make more sense in a second here, a set of strategies among competitors for which no competitor can make a so-called unilateral improvement in their own outcomes. And what I mean by that is if you're at a Nash equilibrium, if you're a duck in a patch, as long as no one else moves from their patch, I'm better off staying where I am. So if I see someone else at patch, if I have patch 2 and someone else is at patch 1, if I could get them to swap with me, we'll both be pretty much equal. But if I decide with them staying there to go over to their patch, I'm going to make it worse on me because when we were at equilibrium, we were all getting the same intake rate. But if I go over here, I actually make it better for the people that I leave, and I make it worse for those that I join, including myself. So that's a unilateral move. That's me moving on my own. If I can get someone else to move with me, then maybe I can maintain gains. Maybe I can actually do better for everybody. If I can manage to make a deal with somebody and say, let's just both do this thing, then maybe it's better off for both of us. But if you can't make any deals, if you can't coordinate with anyone else, then you're the only one that can make a move. And the Nash is the point where you don't regret any of your moves. It's kind of like if you were to make any unilateral changes, any movements on your own with everyone else staying the same, you would do worse off. That's what we mean by a Nash. And that, the IFD is an example of a Nash. So questions about that idea? So there's a bunch of social examples that we can describe using these Nash equilibria. So there's one other foraging case that I like to bring up. How many people have heard of the prisoner's dilemma? Seen it in classes? Totally useless. So, but the stag hunt is actually a useful two-player game that is similar to the prisoner's dilemma, but actually matches cases. It's not, the prisoner's dilemma is like for those, like, I don't know, they're kind of like sort of sadists, like who really want things to be really, really bad. And like, if the world was dystopian, how would we ever get out of it? That's kind of like the prisoner's dilemma, but the world is never that bad. And so most of nature doesn't behave like the prisoner's dilemma. But a lot of nature behaves like the stag hunt game. And we actually just talked about wolves hunting, choosing between stags and deer or other things. So choosing between moose and deer, but you could imagine between stags and rabbits, stags and hares. And so it also kind of fits in there. So the stag hunt game, so this is a so-called payoff matrix. So imagine I have two individuals, let's call them two wolves. And one wolf, if both wolves decide that they're going to hunt a stag together, then there will be some benefit, some large benefit, because the stag is big and it'll go to both of them. So this player up here, this wolf that decided to cooperate, will get 10 units of energy, net units of energy. This wolf that's also cooperating will get 10 units of energy. So this is the cooperative case right here. Now, it might be the case that both of those wolves decide that it's just not worth going for the stag, in which case they should just go for the rabbit or the hare. And in which case then they both land down here. And so they both go off and search for their own rabbit. And because there's a limited number of rabbits, then they compete for the finite number of rabbits, but there's still a pretty good chance that they're going to find a rabbit. So they then have to search and use up a little bit more energy because they're both looking for this rabbit. But on average, they both get 5 units of energy for the rabbit that they found. Now, you could have one wolf that thinks the other wolf is going to help them and so decides to go for the stag. And maybe it manages to get the stag and so uses up a lot of energy to take down that stag. Well, while it's hunting for this stag, the other wolf is free to find rabbits, and it's finding a lot more rabbits because it doesn't have to compete with that other wolf. So in this case up here, the exploitation case, you have that one wolf is hunting for a stag. I actually flipped these, so I will in the slides I'll swap these. So this is meant to be up here. This is supposed to be the 8 is going to the one that played hare. So the idea here is that the one that is looking for the rabbit is going to find the rabbit much easier. So it's not going to get 5, it's going to get 8. The one that is looking for the stag, it's going to be harder. So instead of getting 10, it's going to get 1. So, and then the symmetric case on this side where they flip their roles, but one of them's the sucker and the other one is actually finding the rabbit. So that's the stag hunt game. Again, I just need to switch these B's and D's. And where this is the definition of a stag hunt game is this payoff matrix with this relationship. Very similar to the prisoner's dilemma, but this competitive one isn't quite as sweet as it is in the prisoner's dilemma. Now, here I bring this up because this is an example of where there's 2 Nash equilibria. So you don't, like in the IFD, there's one Nash. They all settle out. There's one distribution across all the patches. But here, there's actually 2 Nash. There is this cooperative Nash up here and this competitive Nash down here. So if you both play cooperator and you manage to land there, you're both chasing after this stag, you're both chowing down on the stag, you'll have no regret. Because it's like, this is great. I should not play hare because I am enjoying this stag with my pack mate and we are just doing great. If you both instead decide to eat that rabbit, then you likewise will say, this is fine. I maybe could have gotten more food by going for the stag, but that would depend on the other member going for the stag, and I didn't know if that was going to happen. And yeah, it would have been. And it looks like that other one, did go for a rabbit, so we had to compete a little bit. But I can't control the other pack mate or the other wolves' decision making anyway, so I can't regret giving my 5 units of energy. So I have no regret in any one of these. But if you get on the wrong side of these boxes, then you have a lot of regret. Like, oh, I'm an idiot. Why did I go for the stag? I should have just gone for the rabbit. So even though there are these two Nash equilibria, they differ in a certain way. So this Nash is the cooperative outcome is what we call payoff dominant. So this one, it's much better if you can get your partner to hunt with you. But this one is risk dominant. So it's in this case, if you don't know if your partner is going to hunt, then it minimizes your risk. It minimizes the variance in your outcomes by deciding to just do the safe thing and hunt for a rabbit yourself. So we get these two interesting different outcomes, which makes this, it's a coordination game because it has two Nash that correspond to doing the same thing. So stag, stag, or hare, hare. They're both the same. That makes it a coordination game. But it's a special type of coordination game called an assurance game, where both players agree that it would be better if they both played stag. But they have no way to be assured that the other player is going to play stag. It's an information problem. It's not a temptation problem. That's the big difference from the prisoner's dilemma. The prisoner's dilemma, it's a temptation problem. Why would you would never cooperate in the prisoner's dilemma? It's not just a mechanistic problem. It's like, it's better to defect. But in this case, you really do want to cooperate, but you're just limited by the mechanisms that are available to you. So because you can't coordinate, you can't be assured that the other one's going to play the way that you need them to play, then you're stuck playing the risk dominant one. And so that's what we called it, an assurance game. And overall, what ends up happening is that you end up getting a mixture. There is a solution that mixes. So what that means is that real wolves, if you could model their foraging in this payoff matrix, what game theory would tell us is that a fraction, or one wolf would a fraction of its time play stag and another fraction. So roughly 50% of the time it would play stag, 50% of the time it would play hare. Or roughly 50% of the wolves would play stag and the other 50% of the wolves would play hare. And that mixture would be a stable mixture, either in time or across the wolves. And that's what often happens in these coordination games or even these insurance games. And this also explains a bunch of other public goods problems. National Public Radio, for example, there's a group of people who donate and a group of people who listen even though they didn't donate. That is stag and hare. And that's the equilibrium you get. You can't get everybody to donate, but if nobody donated, then the thing wouldn't work. So you end up getting a mixture of the two. So the stag hunt. But the big reason I brought this up is not only because it involves foraging explicitly, but it's just my point that even though the IFD is a single Nash equilibrium, you can have other social games where you have multiple Nash. And often then the question is, how is the group going to deal with the fact that there are two Nashes? Is there going to be a mixture of those Nashes in the group? How can you get from one Nash to the other, et cetera? In the prisoner's dilemma, there's only one Nash. So again, it's not interesting. The stag hunt, it's interesting because there's two Nash, and then you can ask, how do you get from one Nash to the other? So any questions about that? Does everybody see that that's a Nash and that's a Nash? Okay, so then IFD is a Nash. Big question, does the IFD work? So this is a kind of famous experiment that was first done. So the IFD came from a set of researchers, Fretwell and Lucas. And around that same time, Malinsky, who's a limnologist in Europe, ended up doing this experiment with sticklebacks, these little fish in an aquarium. And he set up this nice setup here where they would drip in little water droplets. And there are a way in which you can condition the culture set up for Daphnia. They're these tiny little crustaceans that these fish eat. Sometimes they're called water fleas. So that you can have pretty tightly controlled that in every droplet of water, you only get one Daphnia on this side. And then in this droplet of water, you get, say, what are it, five Daphnia on this side. And so then you can then adjust the rate of these drops of water. And so let's just assume that they're dropping at an equal rate, but this droplet's got 5 and this droplet's got 1. Well, what would we expect? Like if this is our experiment and the conditions, the assumptions of the IFD hold, what would we predict is going to happen with these sticklebacks? Any guesses? How are the sticklebacks going to distribute themselves around the aquarium? Yeah, pardon me? There's 5 on the left and 1 on the right. Yeah, there's going to be more on the left, right? Right. That's what we would expect. So this illustration is sort of the prediction, is that you would get, let's say, if you put 6 sticklebacks, 6 fish, you get 5 over here, 1 over here, which matches the resource rate coming in. Now, remember, all the sticklebacks are going to be doing equally as well individually, but this group has got more food. So it's a matching of consumers, of producers, of production to consumption. So what actually happens? Well, here's data from that experiment. And so you see initially the fish are figuring out where they want to go. They're kind of going back and forth. This green line here, this is the start of feeding. This is when they turn on the taps and they start dripping in. So there's this little transient case here. This dark green line, that is the prediction from the ideal free distribution. And these are where, on average, because they did a bunch of replications of this is where the average number of fish laid. And so what you do find is that you get this nice split where you get roughly 5 sticklebacks here and 1 stickleback there. So that's cool. Let's make it more exciting. Let's change the feeding in the middle of the experiment. So we initially configure the droplets so that we would get 2 on one of these spots, and then we shift it in the middle of the experiment so it goes up to 4. And sure enough, at the start of feeding, they go down to and they reach the 2 equilibrium, and then they pop up, and then they start going to the new 4 equilibrium. So they seem to be sensing those rates and reallocating themselves to match. Questions about that? There have been a lot of other tests of the IFD. I mentioned ducks on a pond. Around the same time, people did ducks on a pond. So basically what they did there is they did the experiment that I was hinting at here. They had 2 researchers that were holding clipboards, and it was like early 80s, and they were recording how many ducks were in front of them, and then they had a timer that would tell them when to throw breadcrumbs into the pond. And they started out using equal rates, and then eventually they shifted it so that one researcher did with it twice the rate than the other one at throwing in these breadcrumbs. And what did they find? Well, in that first experiment where they had equal rates, then they've got the same. This is the IFD prediction, and these are the ducks initially. Then they start feeding, the ducks come up, and they match the prediction. So based on the number of ducks in the total pond, based on the breadcrumbs that they're throwing out, then they get ducks that converge to that. And then they change it so that now one researcher is throwing out at a faster rate than the other. So now patch 1 is worse than patch 2, and sure enough, it follows the IFD prediction. So the animals do seem to allocate themselves according to the IFD in these experiments. Questions about that? This is a social matching law, just the same as the psychological matching law in operant conditioning. Now, the question is, when doesn't it work? So there are plenty of cases where the IFD does not explain distributions of animals that you see out in habitats. And one of them is in the case of colonies. So there is a phenomenon called conspecific attraction, and that is just a general tendency for certain animals to be wanting to be around other animals. And so this can happen in giant colonies of birds. They all end up aggregating in one spot, not because there's a lot of resources there. I mean, there could be all sorts of reasons, but it's a cue that it's a good place to be to have other individuals there. Cockroaches, sorry, Anushka, cockroaches, when you cause them to scatter, then there's these famous experiments where you can give them refuges of dark. And you can, if you have one cockroach, it kind of goes equally to any one of those refuges. But if once you start getting more cockroaches under those refuges, then the cockroaches tend to go to those refuges more than others. So they not only want it dark, they want it dark and they clustered around other cockroaches. It's kind of interesting. If you know, termites are social cockroaches. So even, cockroaches are sort of the sort of like ancient termite or something like that. Then, they have this sort of latent sociality kind of built into them. Um, so yeah, conspecific attraction, that's one way that you're going to get aggregations that have nothing to do with food. And that might perturb some of your IFDs as well. The other thing, as I mentioned, the IFD assumes that everybody has equal competitive ability. That is often not the case. So animals arriving early to a resource may be able to defend the resource and keep out all other animals. And Fretwell and Lucas realized this, and so they built another predictive tool, another model, which I'm not going to go into. But if you're interested, you can look this up, the ideal despotic distribution instead of the ideal free distribution. So if you're a despot, if you can grab the resource and keep everyone out, control who comes in, then the question is, what will be the equilibrium distribution across the pond or across whatever the habitat area is? And this it models the competitive asymmetries and the resource differences and blends them together to predict what this distribution is. So this is sort of a general version of the IFD to include those differences in competitive ability. And then there's just sort of things that are related to that. Some animals might have better information about patches than others. And so some just have more experience. And so they're able to read cues better than others. And so some can tell that one patch is low quality without having to visit it, while other ones can't. And that can kind of perturb this off. And so in these experiments that I was showing here, these are huge confidence intervals. So it's not quite as pretty. Like this back here, the Malinsky one, I borrowed this from Lee Dugatkin's book. I was going to go directly to the Malinsky paper, but when you look at the Malinsky paper, Dugatkin only put the means here because the confidence intervals are so large that it's not immediately compelling when you look at it, because it's just like a block. It looks like it's basically grid paper. But if you look at the means, then it's there. But so Dugatkin just got rid of the confidence intervals and just put the means, and it looks much more compelling that way. And I think the ducks on a pond, even with the confidence intervals, is pretty convincing. But still, there's quite a lot of noise in here. So there's quite a lot of opportunity for the IFD to explain a little bit of the variance, but certainly not all of it. So, and then there are other reasons why you're going to get perturbations in habitat choice off of the IFD. All right, so that's the IFD. So any questions? Social matching. Cool, all right. We talked about exploitation, talked about competition, a little bit of cooperation with the stag hunt. Things get pretty interesting. Now, a lot of times talk about cooperative foraging. People are attracted to charismatic megafauna. They talk about dolphins and all what the wonderful things dolphins do. Yeah, I mean, dolphins have got a lot of interesting sensory abilities. They're mammals, yada, yada. And they do some cool things. But to me, the really crazy cooperative foraging stuff happens when you've got high relatedness, because then you've got the opportunity for natural selection to start crafting these odd solutions, which you can't explain with these Nash equilibria and stuff like that. Like these Novomessor cockerelli, which are local ants you can find right here in Phoenix. Go to South Mountain, great colonies of Novomessor cockerelli. You can see this is a fig that they've never encountered fig before. They just grabbed it and carried it in basically a straight line at a constant velocity. They certainly have never seen this object before. Had no trouble if you layer it with fig, you coat it with fig, they pick it up and they carry it all day long. And even at the end there, they managed to anticipate this rock was here and move around the rock. So that's pretty cool. There's these other interesting examples like this Leptogenes colony. They actually form chains out of their bodies. So here's a sort of a version here where you can see that there's two chains. So there's two ants that are connected to a giant like millipede, and then they connect to each other and they form these giant tugging chains, and they can carry things up walls and so on. So these are individuals that are not acting on their own. They're not distributing because they're get equal intake. These are individuals that are cooperatively trying to maximize an intake rate to a colony elsewhere. So I think that's pretty cool. So when you start getting these high levels of integration, it starts making you wonder, who is the individual? And that kind of brings up my last example here in these fire ants. So Solenopsis invicta, the red imported fire ants, this applies to other Solenopsis congeners as well. They're notably bad at trail following. So if you find a fire ant colony, they don't follow a tight trail. They kind of are like very fuzzy around that trail. So this is in a paper by Ed Wilson. These are kind of some sample paths of trail followers here. So if you have an individual, she'll go out. And so there's a bait. So she went out, she found a bait, and then she went back home. And then you can watch her as she comes back out to look for the bait. And you can see this is like the variation for the same, like there's just a whole lot of, so like the dark line and the gray line, there's just like a lot of variation for the same trail. You don't send ants in the same spot. And so for a while, people thought that it was just a mechanistic limitation, that fire ants are bad at pheromone communication. They're just bad at trail laying. That's for a while what people thought. But Ed Wilson noticed that, well, actually, if you look at the end of these trails, so these are locations where the recruits turn back. Here's where the original bait location is. You get this kind of large area. So basically, you found a juicy prey item, you lay a trail back to the nest, you wait for individuals to come back. Some individuals come here, some individuals come here, some individuals go, but you basically distribute a bunch of individuals over this area. And what Wilson was saying is like, is this bad or is this good? Like it would be bad if the function here was you're trying to bring individuals back to this location. Then you had all these misses. So you're gonna like be sending out all these scouts into the wrong location just because you have like crappy communication. But then the thought was, sometimes these voracious fire ants actually recruit to live prey that is still kicking, like crickets that are actually trying to jump. Crickets are saltatorial, they jump away or trying to crawl away. So you get a couple of fire ants there, some that are trying to subdue the prey and some that end up leading a trail back. And what Wilson noticed was that oftentimes this wide distribution of ants was so wide that when a cricket tried to jump away, that cricket would jump into another spot where there were already fire ants. And then those fire ants would attack the cricket and then start laying a trail to that spot. And that would shift this whole football over so that it was now centered on the cricket there. And this will go on and on until eventually this cricket was subdued. So the question really sort of became, well, I can sort of illustrate this. So you find juicy morsel, you come back, you end up laying a trail that brings a bunch of ants in a distribution around the center of where you found that juicy morsel. So now you've got most ants are right where you found it, but there's some ants out here, and there's some ants out here. That little morsel is still alive, so it sort of jumps away, but there are still plenty of ants that are still out here. So the thought was actually, maybe this is adaptive. Maybe the ants aren't communicating where the prey was. Maybe they're communicating where the prey will be. And maybe natural selection tunes how fine they follow this information, this pheromone trail information, based on what type of prey they forage on. And if it's moving prey, then maybe they actually have worse communication because they spread things out, because there's more of a chance that that prey is going to jump away in these directions. But if it's stationary prey that's not going to move, then maybe that explains why other ants are really good at just following the trail with high fidelity. So, when I look at this and I think about those explanations, are there any questions about that before I make the next leap into hopefully not fire ants? So when I look at this, then it makes me sort of start wondering other kind of silly questions. Like, to me, this looks a little bit like a diffraction pattern. Like, it looks a little bit like I aimed some light in a slit and then it distributed that light in this sort of interesting wave pattern here. So it's almost like the pheromone trail ends up creating this sort of distribution here. And but in order for me to interpret like light, it's a photon. So the photons show up, some photon shows up here, another one here, another one here, another one here. But in reality, what we experience is not every photon. We experience the wave. We experience the thick green lines and the thin lines. We experience the whole thing together, the ensemble. And that kind of makes me wonder, is an ant a particle or a wave? So when we think about these very tightly integrated social foragers, sometimes maybe the individual is not the individual. Maybe when we're applying our rules of thinking about social foraging, maybe this isn't social at all. Maybe this is actually a single individual that is the colony. And that colony we should apply solitary foraging ideas to, as opposed to applying social foraging ideas to its individuals, because these individuals are pretty bad foragers, but the group is a really good forager. So that's what happens when you get kind of hyper cooperation. So, at some point, you might get a lifting of individuality to a different level. And that's the idea that I want to kind of leave you with. So, any questions about that? Okay, so that's all I've got for you. We're done with foraging and moving on to mate selection, I think. So I'll get those things out for you. I'll add the other drops. I hope that's enough sort of payment for my mishap there for not getting those out. And I'll give you credit for coming today and even get you out a couple minutes early. So let's start a poll. All right. So question is, in the IFD, what is the I? So what word is the I representing in IFD? And that's all I've got for you. So have a good weekend, and we'll see you Tuesday.